In this video, we're going to talk about the null space of a matrix. This has a fancy name, but it's just the set of vectors x, so that a times x is equal to the 0 vector. I like to think of this as all vectors that are squashed by multiplying by a. You can also see it as the set of all solutions to the homogeneous equation ax equals the 0 vector. So we've worked with these before. Let's try this out by finding the null space of this matrix A. So what we're going to do is we're going to solve ax equals 0. Okay, so as before, as always, we write down a matrix. When we have a homogeneous equation like this, we often don't include the augment and the zeros, but I will this time. Okay, so now we use row reduction. We replace row 2 with -1/2 row 2. And this gives us 1, 2, 0, augmented with 0, 0, 1, -1/2, 0. We're going to replace row 1 with row 1 minus 2 row 2. So we're doing that back substitution. And at this point, we have our matrix in reduced row echelon form. We see our pivots marching to the right. They're all equal to 1, and they have zeros above and below them. Okay, now let's translate this into linear equations. So if our first column represents coefficients for x, and our second column represents coefficients for y, and our third column represents coefficients for z, this translates to x plus z equals 0, and y minus 1/2 z equals 0. And z here is our free variable. It's not a pivot. Okay. So we can solve for x and y in terms of z. X is equal to -z, and y is equal to 1/2 of z, and z is free. So the null space is going to be every vector x, y, z that satisfies these three equations. Two equations, and z can be anything. So I'm going to write null of A as the set -1, 1/2, 1 times z, for z a real number. Notice this is these are all just multiples of one vector, so this represents a line in R3. So you see that we already have lots of experience with finding the null space of a matrix. All we're doing is solving the homogeneous equation and writing our solution in parametric form. It can be helpful while we're doing this to keep in mind where our null space lives. So in this last example that we looked at, we had a matrix that had 2 rows and 3 columns. And when we were writing out solutions, we said, okay, the first column represents coefficients of x, the second column represents coefficients of y, and the third column represents coefficients of z. So solutions are going to have the form x, y, z. That That is, they're going to live in R3. Similarly, in general, if we have an n by n matrix, the number of columns n tells us the size of the vector in the null space. So the null space is going to be made up of vectors in Rn. Let's take a moment to practice the definition of null space. Please pause this video while you decide whether or not the vector 1, 3 is in the null space of A. So there are a few ways to proceed, but let's remember our definition. The null space is a set of vectors so that A times that vector gives us a 0 vector. To decide whether or not 1, 3 is in this null space, all we need to do is multiply A by this vector 1, 3. This gives us 10, 20, and negative 30, which is not equal to the 0 vector, and so it is not in the null space. If you want a little bit more practice, you can consider whether or not the vector 3, negative 1 is in the null space of A. Okay. In order to find a basis for the null space of A, all we're going to do is solve AX equals 0 and write our solution in parametric form. For each free variable, we're going to have one vector, and these vectors form a basis for the null space. So the dimension of our null space is just going to be given by the number of free variables. All right, let's try this out with an example. So here we have this matrix A. It has 3 rows and 4 columns, so it's a 3 by 4 matrix. And what we're going to be doing is finding a basis for its null space. So first off, let's figure out what space this is going to lie in. So we have columns for variables x, y, z, and w. So those are 4 different coordinates. So null space of A is going to be a subset of R4. Okay, we're going to proceed just by doing our normal row reduction until we get to the reduced row echelon form. So I'm going to start by looking at this first pivot, and I'm going to clear out all of the values below it. I'm going to pause as we go through this so that you don't have to sit through the gory details. Okay, and at this point, so we've got this one pivot, below it are all zeros. We have another pivot. We can see that row 3 is just a multiple, it's the same as row 2. So we can replace row 3 with just zeros. And at the same time, I'm going to multiply row 2 by 1, by negative 1 rather. So we're very close to the reduced row echelon form at this point. The only thing that is missing is that we have this non-zero value above our second pivot. So we're going to clear that out by subtracting row 2 from row 1. All right, and now we're in the reduced row echelon form. What we're going to do next is translate this reduced row echelon form into linear equations in terms of these coordinates x, y, z, and w. You can see here that we have 2 pivots. That means that z and w here, which are columns without pivots, are going to be free variables. This tells us that our null space is going to have dimension 2. Okay, so let's get to work rewriting these as linear equations. We get that x plus 2z plus 3w equals 0, and that y minus z plus 2w equals 0. And z is free, and w is free. Okay, now I'm going to solve for my pivot variables in terms of the free variables. I get that x is equal to negative 2z minus 3w, and y is z minus 2w, and z is z, and w is w. Okay, so the null space of A can be written as all vectors that have this form negative 2z minus 3w, z minus 2w, z and w, where z and w are real numbers. All right, this gives us a full description of the null space. If we want to find a basis, though, what we're going to do is separate these out. We're going to separate these two variables. Okay, so what that looks like is I'm going to pull apart all of the pieces that have z's in them. So I've got negative 2, 1, 1, and 0 z's. What about w's? I've got negative 3, negative 2, 0, and 1 w. Okay. So these are the vectors that are associated to the free variables. So these two vectors make up a basis for our null space. And that's it.